Okay, so today's lesson is graphs, charts, and tables. And what I mean by that are any possible graphs with axes, any charts or tables that they might provide to you that you may have to analyze. And so this is a wide ranging of things from gas laws to reaction rates to titration curves to NMR, IR, and mass spectra. And so we're going to kind of go through all these things. We'll talk about trends also, a lot of different things where charts and graphs really come to play. And interpreting them correctly allows you to kind of reach the correct conclusion for multiple choice or straight answer questions. And we'll kind of go in order from topic 1 all the way to topic 11. I think that's the best one to kind of end on. And so the first one is a topic 1 idea, which is gas laws. Okay, and understanding the relationship between pressure, volume, and temperature is really important graphically. And so what I find is that if you understand the combined gas law, P1V1 over T1 equals P2V2 over T2, you can kind of come to the conclusion of what the graphs are going to look like. For example, and again, you don't need to know the name of Boyle's law, Charles' law, and Gay-Lussac's laws. It's just a general relationships between pressure and volume and temperature. And so when you're going pressure versus volume, you have an inverse relationship. Because when you look at the equation, P1V1 equals P2V2, if pressure goes up, volume has to go down because they have to be equal to each other. And so what you see here is a pressure versus volume curve that looks like this. Okay, an inverse relationship, y equals 1 over x. Okay. Now, the IB is also known for sometimes linearizing equations to make sure that you actually understand what's going on, like that you don't just memorize P versus V. And so sometimes they will find a relationship that makes it linear. For example, P versus 1 over V. That would be a linear relationship because, like we said, it's an inverse relationship. So if one value is inverse, then it's a direct relationship between the two. So understand that there are possibilities where they might say, which of the following axes are appropriate for this linear graph? And you may not see anything else that's linear, but you may see something that is tweaked to generate that linear line, for example, like that. V versus T and P versus T are direct relationships. So when one increases, the other increases by the same factor. And so with that, you just have to be careful because the important part, whether it's P or V versus temperature, is that this graph is only generated like this when it's in Kelvin. Because at 0 Kelvin, there is 0 pressure and 0 volume. What you have to be careful about is if the axes are not that, let's say, for example, it's temperature degrees Celsius, then your graph actually intersects the y-axis at a higher point because it will intersect the x-axis at negative 273 degrees Celsius. So understand that the graph does shift when you graph it in terms of degrees Celsius, and read those axes very carefully to make sure that you're getting the right result for the graphical trend. And as a side note, this isn't really a graphical thing, but you do want to understand that real gases deviate from ideal at low temperature and high pressure. Okay. And why that is because low temperature means slower speed, which means IMFs are more effective, meaning that the forces of attraction between the molecules and repulsion are more representative in that scenario because the molecules are passing more closely to each other. The gas particles are are interacting with each other for longer periods of time, so the attractions and repulsions are actually more effective. With high pressure, that is important because the volume of gases is taken into account now, because once you get to high pressure, that's a really, really small volume, or there's a lot of gas particles in that volume, which increases the pressure. If that's true, then there's less empty space, and now the volume of the particles actually significantly affects the amount of empty space in the container. So that's going to significantly affect your volume value, and that's why ideal doesn't really work at those conditions. Okay. Topic 2, okay? The next kind of chart graph that we're going to talk about is the line emission spectrum of hydrogen. Okay. And the IB likes to kind of represent this in a couple different ways, and so really understanding each form of it is important. The main form of this is the idea that in its ground state, an electron for hydrogen exists on the first energy level, But hydrogen does have these other available energy levels to access that aren't occupied by electrons. And so the emission spectrum happens because when you excite that electron, it jumps up to a higher energy level. And then what happens once it has kind of seen through its excited state, it returns back to the ground state, the lowest energy state. Okay? And that is our emission here, because it must release that excess energy it had when it got to its excited state. So that's released as a photon, as light. And what we'll see is that this tells us a lot about the electron energy levels in an atom, because if we measure these values, yes, the energy keeps increasing, but the difference in energy in which it increases is reducing, which tells you that at higher energies, levels converge. They get closer and closer together, so the difference apart is shorter, which means there's less energy required to reach the next kind of level of a jump. Okay. Which also means kind of the jumps down to the first energy level are the most significant in energy. And this is where your UV light, which is the highest of the kind of relative electromagnetic spectrum that we have, between infrared, visible, and ultraviolet. Ultraviolet is the highest energy. Going down to 2, is visible. And then going down to 3 is infrared. So that again supports the idea of these energy levels that are discrete, because you're only getting specific energies of photons released. If they weren't discrete energy levels and the electrons could be anywhere, then you'd get a continuous spectrum. You wouldn't just get specific lines, you would get every single possible line, because the hydrogen electron could be in any energy state possible. But we don't see that. We see discrete energy levels. Now, before we translate this into a different graph, there are a couple other concepts that you need to be kind of aware of on this spectrum and using this illustration. The main one, I think, is going to infinity, okay? And that represents ionization energy. So going from the ground state in hydrogen, that be n equals 1, to infinity would take a certain amount of energy, okay? Now, every element that varies, right? Because hydrogen only has one energy level with one electron in it, so the ionization would have to leave from the first energy. But elements in the next period would lose from the second energy, so they would jump from here and out. So don't always assume it's the first energy level, it's the outermost energy level for that element. Hydrogen happens to be 1, but for many other elements like lithium or like carbon, that's energy level 2. For sodium and sulfur, that's energy level 3. So don't always assume it's energy level 1. Okay. Now, another way the IB likes to represent this is kind of in this spectrum where they show like high energy and low energy, and they show the lines that are being emitted by the emission spectrum. And so the emphasis here you want to keep in mind is that as you increase jumps, the higher energy does increase, but it converges. So if you're going to reflect this, it's going to be low energy, and then a big jump, and then a slightly lesser jump, and then a slightly lesser jump, but you're still going to increase. And the IB can label this a lot of things. They might say it's called higher energy and lower energy. They might say high frequency or low frequency, you know, to test students on whether they understand the relationship between frequency and energy, or make it even more challenging and do a short wavelength and a long wavelength, okay? That relationship between all those three concepts can be illustrated on these line spectrums. So it could be any of those three scenarios on that spectrum, and you'd still have to make sure the lines converged at higher energy levels. Questions about any of this? Okay. Let's see. Along this same topic, I would know the general shape of S and PX, PY, and PZ orbitals. It's not so much as a table or chart, but I guess it is technically a graph, because you have your axes for your S, and then you have your axes for your P orbitals, right? Because they are labeled PX, PY, and PZ because they exist on those axes. And so knowing that it's a dumbbell shape that bisects, or actually maybe not bisects, that is along the axial lines of X, Y, and Z, is something that you are expected to know. Okay. Now, this next chart has to do with ionization energies, and I know we talked about this in class, but I want to make sure that it's kept in mind here to talk about how this data tells us a lot of information about this. And this is mostly higher level, but I think everyone can help kind of benefit from understanding these concepts for that. And so these are the ionization energies for the first 20 elements. Their first ionization energy and then their successive ionization energies from left to right. Okay? And we're going to talk about this table in two forms. The first form is talking about just the first ionization energy levels and how that proves, I'll keep this in green, how it proves the existence of energy levels and sublevels. Because what you'll notice is every time you go to the next energy level, there's a huge decrease in ionization energy because you've added another energy level, which weakens the attraction to the electron, therefore it takes a lot less energy to lose that, despite gaining a proton in this manner. Okay, so those lines there represent the energy levels. You know, this is n equals 1, n equals 2, and n equals 3. Okay, but even within those energy levels, you'll notice a slight decrease, a lesser decrease, but a slight decrease within that energy level. And that happens here and here. Okay. Oh, sorry, I missed the energy level 3. Let me fix that. And this is energy level 4. Okay. So that light green line represents a change in sublevels. So you notice now you have the S sublevel and the P sublevel, the S sublevel, and the P sublevel. So those ionization energies help support the concept that, one, energy levels are away from each other in an atom, and two, even within that energy level, the electrons aren't all on the same energy. Some are at a lower energy state than others, which represents the sublevels, S, P, for ionization energy at least. You're not really going to lose d electrons for the main groups of elements. And so that first column kind of proves that. And the IB will take that information and give you like snippets of it and see if you can kind of show that. Now, I'm not going to talk about the slight other dips like nitrogen to oxygen yet. We'll talk about that in trends. But this is just to prove the concept of why energy levels exist and why sublevels exist and how we experimentally prove them. Okay. Now, the pink that I'm going to draw is how successive ionization energies of an element help explain the electron configuration / valence electrons. So looking at a single element's successive ionization energies, for example, boron here, okay? Now, they will always increase. Like successive energies will always increase because you have the same number of protons and you're losing electrons. So therefore, the attraction for the remaining electrons always will increase. So there's never going to be a time where the successive ionization energy dips. So keep that in mind. But when you're looking at a sample of successive ionization energies, the largest gap, the largest jump by number, not by factor, but by number per se, okay, like by actually subtracting two values, that represents the change in energy level. That represents the difference in distance to the nuclei from that energy level. And so you see here, boron has the biggest jump from 3,660 to 25,000, which means the fourth electron is in a different energy level than the third electron. And so what that tells us is that boron has 3 valence electrons, and that's what you're using that information to do. And so when you look at successive ionization energies, you're looking at, how do I explain how many valence electrons there are? Because I should see a big jump after having lost the last electron in that energy level, and that's where you see it for boron, and you see it for things like carbon as well. Carbon, you'll notice, has a huge increase after 4, which makes sense because carbon has 4 valence electrons. And so that's what that part of the chart is really kind of telling you about that. And that will also tell you the group number, right? Because the number of valence electrons coincides with the group number. So boron is in group 13, okay? Carbon is in group 14 because it has 4 valence electrons and 3 valence electrons as well. Okay, questions so far? Let me see if I have this. Because I might have to move it. Okay, let me actually take this. Pauses. Let me take this from another. Give me 1 second. I'm gonna save this, send this to my Notability. Wait, what's going on? Actually, that one's not useful. Okay. Okay. The thing with where's the graphs import? Okay, right there. Okay. Wait, I'm missing one. Oh, here it is. The thing with trends, okay, the thing with trends is that knowing the explanation for trends is good for a short answer, and explaining why things increase and why things decrease is very useful. On the multiple choice, on the other hand, what they like to do is to graph out these trends and have you identify which trend is which one. And so it's important that you look for certain things on the graph to notice whether you are on what trend you're talking about, okay? Now, these graphs are from a lab that I did in 11th grade for topic 3, where you were given all the data and you had to plot them out. Now, there's some gaps in here because part of the lab itself was to predict those values, but that's okay. That's not the main idea here. With atomic radius, we know it decreases as we go across the table, and it's pretty consistent as we go across the table. And the highest atomic radius will be the beginning of each energy level. And so this is like lithium, and this is like sodium, and this is like potassium. Okay. This section here, your transition metals, because with those, because you are adding inner inner electrons and protons, the radius doesn't significantly change that much. And so you'll see those sections here, and you'll see that kind of continuous decrease in atomic radius until you get to the next energy level, and then it goes back up. Ionization energy, we know that the highest ionization energy happens on the right side of the periodic table, where you have the most protons for the same number of energy levels, which means the most energy it takes to remove an electron. And so the peaks here represent different elements. This is helium, this is neon, this is argon. Okay, and so now the peaks look a little bit different than they did before. And with ionization energy, you'll see certain exceptions in these graphs that you have to really be careful for. This is kind of the niche things that students don't think about doing because they just memorize the trends and they don't actually think about what the values mean. We talked earlier that there are some exceptions to the rules because generally ionization energy does increase as you go across the periodic table. But the thing is, that doesn't take 100% into account the electron configuration or the distribution of electrons in the orbitals, because that does actually have another effect. And this difference here is like beryllium to boron and nitrogen to oxygen. And those are the main examples that they're going to talk to you about with this exception. Now, you can go to the next set of elements as well and see that, but usually the period 2 is sufficient to kind of show that. And these exceptions rely on the electron, the orbital diagram. So if you're trying to explain these, you're going to have to think about the orbital diagram and how they're different. And so, like, for example, nitrogen versus oxygen, its 2p sublevel looks like this. And so oxygen removing its 4th electron allows for a half-filled subshell, which minimizes electron repulsion and allows it to be at lower energy states. So there is more energetic incentive for oxygen to lose its electron than nitrogen is, which already has the minimized repulsion, and it would destabilize the atom if it were to lose the electron, because now the electrons would not be imbalanced in their orbitals. And so that's why you see that dip there. You also see the dip in boron because of that energy level difference, right? Because beryllium has 2 in the 2s, boron has S2S2, and then S2P1. So that electron, in emptying out that sublevel, actually minimizes the energy state, which makes it easier to lose than losing from a full 2s. And so really pay close attention to these graphs. If you've taken some mock exams, you've seen some of these graphs on the multiple choice, because again, it's how the IB really makes sure that you understand trends and that you're just not saying, oh, they always increase, they always decrease, left to right and right to left, etc. It's really understanding each individual atom's trend within that that series. So with ionization energy, you'll see dips, okay? And those are really important because I've seen some difficult questions about that, and about trying to identify the atom or the element in question based on a small section of that ionization energy. So yeah, if you also, you can add in that this would be your lithium, sodium, and potassium, and then again, here are your transition metals. I don't think they'll show you this entire graph. I think they'll just show you a subsection of this graph so that you can determine information from it. Now the last major one is electronegativity versus atomic number. And so this one, on the other hand, does have blanks intentionally. So this is not part of the lab. There are intentional blanks for missing elements because electronegativity is the attraction an atom has for a shared pair of electrons, which implies that it has to be bonded to be able to determine that. And so you'll notice that you're missing helium, neon, and argon from this because being small noble gases, they don't bond. Now, larger noble gases do bond in expanded octets and stuff like that, but that's not the point here. The idea is, yes, the general increase from the left side of the periodic table to the right side of the periodic table occurs, but you get more issues because there are actually gaps in this graph. And so when you see gaps in the graph, that's usually a kind of a sign that you have electronegativity here, because or maybe electron affinity as well, but electronegativity, especially as you go up. Electron affinity is not as much of a trend. I think it would be harder to graph electron affinity than it would be electronegativity. So your odds are that if it's steadily increasing but you're missing the noble gases, that should be your electronegativity chart. And this being 4.0 is fluorine, and then chlorine. And then I think bromine's in here somewhere as well. It might be the very last one here. Wait. Yeah, 35 is bromine. Okay. So this is a different way the IB tries to present this information to see if you really understand it. So like I always do, I will sync this into the Dropbox. So if you want to print these pages out with these graphs or for your study guide, that's fine. And so yeah, these were graphs that I generated from the lab just so that there were like standard values. That's why there's AT next to it, because you had to put your initials next to the title. Okay. Questions so far? We kind of skipped through a little bit, and this is a chart and graph, but this is also this is a chart and graph from the data booklet. And so I'm going to pull up the data booklet and take a couple screenshots of this to include this into our oops. Okay. Oh, I need this other one just up here. Okay. Now, this here, I'm not going to go into calculations for this because that was another video, but understanding a couple of concepts about these charts is really important. And here, these are all bond lengths, okay? And the main idea I want you to take from this is the fact that as you increase bonds, okay, the increasing number of bonds decreases the bond length. And so if you've got a double bond or a triple bond, the triple bond's always going to be shorter than double bond. And if you notice, benzene has kind of 1.5 bonds because it has each single bond and they share double bonds across everything. So there's 3 double bonds shared across 6 bonds, so that's about half a bond each. Okay, let me kind of write that down. But so, like for benzene, it's essentially 9 bonds for 6 places. So therefore, you have about 1.5 bond strength, which means the bond length will be between a single bond and a double bond, which makes sense here because a double bond is 134 and a single bond is 154. So 140 is kind of right in the middle, well, a little bit closer to double bond, but it's right between those two. And they could have you predict the bond length using information from this table to determine that. Ozone's another good example, right? Ozone has a 1.5 bond because there's a double bond that goes back and forth between 2 spots. So it's 3 divided by 2 is 1/2, 1 and 1.5. Well, ozone to ozone has a bond length of 148. And oxygen to oxygen single bond has a bond length of 148. Oxygen gas, which is double bond, has a bond length of 121. So if they ask you to estimate the bond length of ozone, you would guess somewhere between 148 and 121. If you go right in the middle, there'll be a range of acceptable answers. But so just understanding that the bond length decreases when you have more and more bonds between the 2 atoms. Bond enthalpies, same way. Make sure that you're able to A, read this cross table, and B, make sure you're looking at the right bonds. A lot of the time, students make huge mistakes because they forget N2 is a triple bond. They forget O2 is a double bond. They forget CO2 has 2 C double bond O's, you know? And so all the ones in the table up here are single bonds. Everything that's a multiple bond is at the bottom outside of the cross table. So make sure you're finding the right value for each of these things. Okay. Questions about that? Okay. All right. We're going to go through topic 5 and 15, and then we'll probably take like a 10-minute break, and then we'll resume. We're making fairly good time, but I think we'll slow down a little bit in the topic 11 and 21, the very last section. Okay. This topic has a lot of graphs and things like that. Topic 5 and 15, energetics. Okay. Now, the first graph that you may end up using is a calorimetry graph of temperature versus time. Because when you measure calorimetry, because the reaction doesn't happen instantaneously, it happens over a period of time, we measure the change in temperature over a period of time. And what you'll see is what I had here. Oops, hold on a second. I swear I had it here. Hold on a second. saw it earlier, I thought. Okay, I guess not. But so, what you'll see is usually these are exothermic reactions or endothermic, whichever one is the case, but usually they are exothermic. And you'll see this scenario and then go up and then cool down. And this graph shows you the change in temperature and key things that you want to focus on here. Okay? This point, for our purposes, is the initial temperature, right? Because the reaction doesn't start until temperature actually changes. So usually what the labs will have you do is wait 5 seconds so you standardize temperature and then add the other reactant so that reaction occurs. And so this reaction is giving off heat. So it is increasing in temperature. But in a practical lab, when you start releasing heat, some of it's lost to the surroundings and the water tries to cool back down. Hence this kind of reverse, the decreasing linear trend at the end, because the reaction is already finished and now it's just starting to cool down. Okay, and so what you'll do is to minimize that. Is that oftentimes we'll draw a tangent line to that cooling curve part, and then extrapolate what the final temperature would have been if the reaction had happened instantaneously. Okay, so you will be given a ruler, so you may have to manually do it. Sometimes they give you the equation of this line so that you can plug values in. And so whatever time it started at, you plug that in for time, not 0, but the time that the reaction started. And so this allows you to solve for the change in temperature for calorimetry. So understanding this graph, again, with endothermic, it would just dip downward and you'd still be drawing the tangent line to the heating curve in that case and finding the final temperature. So either way, you're still using this value to be able to calculate this. Okay. Next diagram, okay? Potential energy profiles / reaction energy diagrams. They are slightly different. The reaction energy diagram kind of has more stuff in it, like the activation energy and stuff like that, but really, they're really serving the same purpose. And we'll talk about that a little bit later as well in kinetics. But the reaction energy profile is enthalpy versus progress. And this is where you see that difference between reactants and products in different reactions. Okay, and so that is where you see this energy change here. So this is what a potential energy profile or reaction energy diagram has. And so observing the difference between the reactants and products is the main idea of this. The pathway does not matter. It is just the state of energy of the products and reactants, and whether it's exothermic or endothermic, this one being exo, this one being endo. And in this scenario, products are more stable because they have a lower enthalpy. And in this scenario, the reactants are more stable because they have the lower enthalpy in the reaction. Okay. Questions? I'll leave this here. Energy cycles. This is something the IB likes to kind of illustrate because they think it helps visualize the idea that reactions can add together to get the same overall delta H. And I'm going to use a higher level example here because I think it works best, but this is also standard level as well, understanding energy cycles. And the one we're going to focus on here, we'll also do the Bourne-Haber cycle next, but the one we're going to focus here on first is the enthalpy of solution. Okay. The enthalpy of solution is when a solid goes into its aqueous ions. And so this is our delta H solution, SOLN. But you can also go a different pathway to achieve that same value. You could convert this into gaseous ions, which is what we call lattice enthalpy. And then we could convert that into aqueous ions, which we call hydration. Now, this is something I kind of thought about, which I thought made it a lot easier because I was working with a student a few weeks ago, is that with energy cycles, all you have to do is draw an arrow from point A to point B, reactants to products, and whatever other arrows you have in that way, they just have to match that direction. So, for example, enthalpy of solution could be this, or it could be this, because enthalpy is a state function, so it doesn't matter the pathway, you're going to get the same value. And so notice that my bottom arrow, my curved arrow, this arrow is the right direction, this arrow is the right direction, and this arrow is the right direction. So all you would have to do is add those values together to get the enthalpy of solution for this reaction. Now, if an arrow is backwards, then you have to change the sign. You have to flip the sign so that the arrow goes the right direction. But I find visually that's the easiest way to do it. Just draw an arrow from where you want to start to where you want to end, and then look at all the arrows you have, and then figure out what's missing there. I think that's the easiest way to do energy cycles. And this shows up a lot of multiple choice questions with no calculator because they'll be like delta H1, delta H2, delta H3. And so it's just a matter of drawing the arrow and making sure all the arrows add up to that arrow. Questions so far? Okay. The Bourne-Haber cycle. You are responsible for knowing group 1, group 2, oxides, and chlorides. What that means is you can be given any group 1 or group 2 metal bonded to any to a chloride or an oxide, and you'd have to be able to do this reaction. Okay, and there are only a couple things that actually matter when this is occurring, and so you have to kind of be careful about these values when you're solving them. For example, I'll do one that's kind of different, and so again, this is an energy cycle really. Let's say you have the production of sodium oxide. That's your enthalpy of formation. Okay. Now, with this, to make the solid, you have to somehow get the ions, which is lattice enthalpy. Remember, lattice enthalpy is going from solid to gaseous ions. That's why I drew that arrow in that direction. To get from the left to that peak over there, you have to do several things to these substances to get there. One, you have to atomize by converting sodium into its gaseous atom. Now, again, what you have to remember is because there's a coefficient of 2, this is going to be 2 times the atomization because it's 2 moles. Because every value that you're given in the IB data booklet or you're given in a problem is per mole. So therefore, if you have more than 1 mole, like 2, then you have to double it. If you have half a mole, you have to have that value. But everything's per mole, and that's something you have to really pay attention to with the units. Which then means that if you're going to ionize 2Na, then that's 2 times your ionization energy of that species. With oxygen, you've got to break those bonds. You've got to atomize or use bond enthalpy. Usually, you'll refer to bond enthalpy because that's in the data booklet already. They don't usually call it atomization for like breaking bonds. So with bond enthalpy here, this becomes O, gas. But because it's half O2, this is bond enthalpy divided by 2 because you only have half a mole of O2 breaking bonds. And then going from O2 minus, that's electron affinity 1 plus electron affinity 2. And that gets you to, oh, why did I write NaCl? I'm sorry. I was thinking about the basic one. Sorry. 2Na and O2 minus. I'm so used to doing it with sodium chloride that I just kind of went on autopilot. Apologies. So once you get to that point, then it's lattice enthalpy all the way down. And this is where, if you have trouble memorizing what the equation for enthalpy of formation is, if you draw out the Bourne-Haber cycle, you can follow my method and draw the arrows, because it's either this green arrow here, or it's this arrow there. And if you notice, all the arrows on the left are going the right direction. The only one that's going the wrong direction is lattice enthalpy, because you're actually doing the reverse of lattice enthalpy. So you would add up all the values, subtract lattice enthalpy, and that would equal your enthalpy of formation. So minimize what you have to memorize, right? Instead of memorizing, well, atomization plus ionization energy plus bond enthalpy plus electron affinity plus negative lattice enthalpy, because those values change based on your Bourne-Haber cycle. Sometimes they're doubled, sometimes they're halved, and sometimes they're negative, and sometimes they're positive, like for electron affinity. It's better just to kind of map things out and then draw your big arrow and then just make all the arrows match that. And so the only one you'd really flip here is lattice enthalpy because it's going the wrong direction. Okay. And electron affinity can be positive or negative, so I wouldn't worry about that arrow as much, because you're still trying to get to, you're still getting to the right point. You're still getting to this in the correct direction. So whether that's negative or positive, that doesn't really matter. But the lattice enthalpy, you are going in the wrong direction for that. Okay. Questions? Okay, we're going to take about a 10-minute break. I'm going to pause the recording, and then if you're watching this later on, you'll just go right into the next section. Okay. So, topic 6 and 16, kinetics. This is rate of reaction, essentially. And so talking about the factors that affect rate of reaction, talking about how the data is going to change based on that information. And so one of the things is really understanding like how we measure rate experiments. And so there's a variety of different ways that we can do it. We can do it as change in concentration versus time. We can measure it as change in volume versus time, like when you produce a gas, or change in mass versus time. I guess that's also gas produced because that's going to escape, which is going to decrease the mass of the container in which the reaction is occurring. I'm going to stick with volume here because I find that to be the most kind of consistent one, the easiest one to kind of measure as well. And so with this is understanding how the graph changes based on your scenario, okay? And so this has a couple of different scenarios here, but like, let's say you have something like HCl plus calcium carbonate to produce H2O, CaCl2, and then CO2. Well, the CO2 is what you're going to be measuring here, okay? Now, let's say that you had a reaction and you had like 100 centimeters cubed of this at 0.2 molar, okay? And you generate a curve like this. Okay. So remember, as the plateaus, you have fewer and fewer reactant molecules colliding less frequently, which is what slows down. And eventually when it plateaus, you've already used up the whole reaction. So keep that in mind about different parts of this graph here. Okay, so the plateau is the maximum amount that you're going to produce. You're not going to suddenly spike up more than that. Okay. And so this would be that graph. Now, this graph produces the same amount of gas, but you've done it at a slower rate. And so if your HCl is your limiting reactant, okay, then what you've now run into is something like maybe 0.1 molar and 200 centimeters cubed, because if the concentration is changing, the volume has to change as well if you're going to produce the same amount of gas. Okay. If you're going to have the same slope, but then it's going to be half, then you're going to run into the scenario where it is still 2.2 molar, but now it's only 50 centimeters cubed. Okay, so the things you really want to pay attention to are this first section here, which is the rate, which relates to your concentration if your acid is your limiting reactant. This section is the moles. So how many moles of gas you're actually producing with your reaction. Now, if you get something like this, here you might say that you have like 0.4 molar and 50 centimeters cubed. Okay. If HCl is your limiting reactant, okay, that's kind of the key thing here. You have to really read the question a lot, because if HCl is your limiting reactant, then that's going to determine how many moles that you can create and things like that. But if CaCO3 is your limiting reactant, then the way you're going to speed up the reaction is not that you're going to have higher concentration of HCl. Well, I guess you could, but well, it's less accurate because a higher concentration, if it's not the limiting reactant, won't be as neat in its transition for the curve and things like that. So what you might have with your limiting reactant here, to increase the rate, you might have a decrease in particle size, which means like greater surface area. That means the same thing. Okay. You might increase temperature. Okay. Because again, you're going to provide more energy for the particles to react more quickly. You could also be like stirring or agitating. Okay. So keep in mind, read very carefully, okay, what's your limiting reactant, and that will affect what could change your curve. And the IB is going to be very particular about this in these questions to make sure that you only get the right answer for that. And so pay attention to what the question's saying about limiting reactants and things like that.
Sure, John.
Yes, Erica.
So is everything that you did in color except for the purple, does that represent if HCl was the limiting reactant, and then
Yes,
is
yes, Erica. Yeah. So everything other than that kind of light purple kind of fuchsia is if HCl is the limiting reactant, because in that case, that the volume and the molarity is going to dictate how much you can make and how fast it's going to happen. If it's not the limiting reactant, then the curves don't work as well because you've actually got an excess of it, and so it's not going to determine the exact shape of the curve. But yes, you're right. The IB is going to try to stay kind of neat about these curves, and with the information that's given, factor that in. And so if they say, given the same concentration of acid, explain why the curve would be steeper. Well, if the curve is steeper, that rate is increasing, which if they've told you that the concentration of the acid is not changing, then that implies something else has to be increasing the rate of reaction. And there's several things that you could be doing. Like we said, greater surface area, stirring agitation, increasing temperature, all those things would speed up the reaction. Yes. Good question. I'm going to draw another small one here just for purposes here of showing how you calculate reaction rate, because you're expected to be able to draw the tangent to a line to figure out the rate. So drawing a tangent to a point on the curve, calculating the slope of that line tells you what the rate is at that instant. So the IB might ask you, what's the instantaneous rate at t equals 10? Well, you draw a line up here, that's 10, and you draw a tangent line to that point and figure out the slope of that. Okay, and that works for all types of graphs, whether it's volume, mass, or concentration. Draw a line tangent to the curve. Instantaneous rate is what we're talking about here. Okay. The next thing we're going to talk about here is the reaction energy profile. Okay. Now, again, with this idea here, what we're going to focus on is that enthalpy versus progress. Oh, we still need to do Maxwell Boltzmann curves. Sorry, I'll do that next. Okay. So with this idea, it's understanding the reactants versus products, and understanding this point up here is the activated complex or the transition state. It's essentially the state which requires the maximum amount of energy needed for the reaction to occur. And so at that point, that's the highest enthalpy state. And so you can calculate the activation energy in both directions relative to that. So you can either go right to right or right to left. Both reactions have an activation energy. And a catalyst lowers the activation energy in both directions. Okay. Equally. So therefore, the amount of energy in both directions is decreased, and so the rate in both directions should increase by the same amount. With HL, you kind of have to add a little bit more to this graph, because for SL, you just have to know that the catalyst lowers the activation energy, provides an alternative pathway. But in HL, you actually have to show that alternative pathway in your diagram. And so what you'll see is something like this. Actually, I don't like that last part here. So this is a multi-step reaction because there's two kind of transition states: reactants, products. What you have to understand is that this step here, is the slow step in the reaction. So that's the one, the slow step is always the part that has the highest activation energy. So the activation energy of the reaction is based on that step. Okay, the slow step, the rate determining step, both those terms. Okay. So the shorter peak doesn't matter in the rate because that's considered what's called a fast step. It's always the highest enthalpy state that determines the activation energy. Questions about that? Maxwell-Boltzmann curve. Okay. The Maxwell-Boltzmann curve is to show the distribution of particles in a sample related to their kinetic energies. And so what you'll see is this could be kinetic energy. Sometimes they'll say speed or velocity, because kinetic energy is directly related to speed and velocity because it's 1/2 mv squared. So they still generate the same type of curve, even though the scaling of the axes is different. Okay. And you can say this as number of particles with the energy. I think sometimes the IB will say like particle density. And you'll see it as a representation of this type of curve here, where it's kind of a modified kind of bell curve to show the distribution of all the particles. And the area underneath that curve is the number of particles in that sample. And as you heat it up, the curve stretches out and as you cool it down, the density the width gets more narrow and the peak gets taller. And the key thing here is to when you sketch these graphs, that the peak shifts and the height of the peak shifts as well. There's no way you can have the same area if it shifts to the right and then still has the same maximum peak. So when the IB asks you to sketch these graphs, they look at one, does the peak shift left or right according to the change temperature? And two, is the peak taller or shorter than the original peak to show that the distribution has spread out or has condensed into a smaller range? So understanding those major things are important for this. The last thing here, activation energy. And when a catalyst affects it, that's when you see that target decrease. And so you will see the number of particles to the right of that line increases. And that means more particles have the right amount of activation energy to meet the requirement of the activation energy to react. And so the catalyst is lowering that. What temperature does, notice, is it does also provide more particles with the energy, whether it's a catalyst or not. And that provides a faster rate of reaction as well, because the area that's beyond the activation energy increases as temperature increases, as the curve widens and spreads out more. Questions about that? Okay. Oops, not SL, HL. Rate order graphs. And so understanding the graphs that produce various rate orders is important. Okay. You have a 0th order. You have a first order. Then you have second order. And there's two major graphs that you have to be able to plot here. You have to be able to plot the concentration versus time, which in a 0 order means the concentration of the reactant will decrease, but it'll decrease at a consistent rate because the rate is constant. Which means that if I wanted to graph the rate versus concentration, it would be a straight line. And that line would be equal to K, lowercase k. In a first order reaction, the concentration does affect how fast the reaction occurs. And the lower the concentration, the lower the rate at which it changes. And so when you graph this, you think of it as rate equals K times A. Now you have a linear relationship. And a lot of that's just algebra, right? Rate equals a constant times X, Y equals X, and that's just that graph here. In a second order, it gets much steeper, okay? Meaning that the rate effect from concentration is magnified because the rate is equal to K times A squared. So this is rate versus concentration of A, and it's a parabola. So knowing these graphs and knowing this allows you to figure out the orders and vice versa. If they tell you it's a first order, you should know those graphs. If it's a second order, know those graphs. Or they could give you the graph and ask you what order it is. So knowing that relationship is really important, especially on multiple choice, I would say. Questions about that? But yeah, really be cognizant of these axes, because the axes really dictate what kind of graph you're going to get. And if you're talking about rate versus concentration, then it's just the exponent that determines what the shape of that graph is going to be like. It's more difficult with concentration versus time because in first and second order, they're both kind of curved downward. But you do want to make a note that the half-life is constant here. T1/2 is constant, meaning that if I pick two concentrations and see how long it takes to have that concentration, and then do it again, and then do it again, the time should always be the same. So if you're having trouble between a first and second, double check using half-life. See how long it takes to go from whatever arbitrary value to half of that value, and then do it again. Doesn't have to even be half of that second value. You can pick any value and see if it halves in the same amount of time. If it does, then that's a first order. If it gets longer and longer as the concentration goes down, then you've got a second order because the rate is decreasing faster than the concentration. Now, just really quickly, I want to talk about calculating rate of order from this table as well, because sometimes you'll have like A and B and then rate, and you may have like 2, 4, 8, and then we'll say 4, 4, 16, and then 8, 8. Does that work also? Or do I want 32? I want 32. Yeah, that's fine. Okay. This is one of the tricky ones given a table where you can't find constants for both exponents. So you can only solve for one of them by using this. Okay. And so we can solve for A because in experiment 1 and 2, A is changing, but B is constant. Okay. And so rate is equal to K times A to the X, B to the Y. So if we plug in all these values, 16 over 8, the K's cancel, 4 over 2 to the X, and then 4 over 4 to the Y. Well, this cancels out. So then this becomes 2 is equal to 2 to the X. So then X equals 1. So A's impact on the rate is first order. Okay. Now with B, because A is not constant anywhere, you have to pick any two reactions where B changes. I'm going to pick the second two. And we do the same thing. This is why I'm doing it, because I know a lot of y'all could kind of eyeball and goes, this doubles, first order is 1. But what happens when you don't have that constant here? You may have to fall back on this plan here, which is 8 over 4 for A, which is raised to the first power, 8 over 4 B, which is raised to the Y power. So you have to remove A's impact on the rate before you can measure B's. So this becomes 2 is equal to 2 times 2 to the y. Well, A already doubles the rate, so that's 1 equals 2 to the y. So B's rate order is 0 in this scenario. B's order is 0 in this scenario. So I tend to, if you can't see how, like on the graphs just right away, this is a fallback plan. Just pick any two experiments, set them divided by each other. The exponents will distribute, and then just solve for it algebraically. It's a foolproof way to do it. There's no problem where if you do that, it won't work. The only catch isn't even in the technique, is sometimes the IB will give you the last column in time. And that's a little bit tricky because rate is equal to 1 over time. So you may need to recalibrate those times into rates so you can actually compare them. Because the faster the rate, the shorter the time. So your multiplying won't work that way. So be careful. If you see time as your last value, do 1 over time and then compare the rates to each other. So just that's a kind of quick kind of word of warning here. Okay. Next thing for higher level. Natural log of K versus 1 over temperature. Okay. Understanding that this will always generate a negative sloped line where this slope is equal to negative EA over R. So the negatives will cancel out in this scenario, but understand that they both have negatives and that's why they cancel out, not because they're both positive. Okay. And understanding natural log of A being the frequency factor. Okay. That's what the one that factors in orientation of the collisions. Okay. So be able to read this graph. I've seen other tests where they say like K versus temperature. That's exponential. It's not linear. Because if it was linear, then you wouldn't need to take natural log of K and 1 over T to get it. So the rate will increase at a much faster rate than the temperature does. I think the rule of thumb is every 10 degrees the temperature goes up, you double the rate. So that's a useful little tip right there. Okay. Questions about that? Again, we're not going into the calculations today. This is all just analyzing and looking at graphs, getting information from them. Okay. Topic 717, equilibrium. Not too many graphs in here. I just want to show you a couple of graphs that might appear. The first one is concentration versus time. And I'm going to do the red as the reactants, and the purple as products. Okay. Now, the product line doesn't have to go over the reactant line. In this example, it does, but doesn't always. Okay. What you need to understand from this is that when they become parallel, that's when equilibrium occurs. Because, let me draw this a little better. Oops. Okay. Because once the concentrations stop changing, that means the rates of the forward and reverse reactions are the same. Because every time you make one molecular product, you'll make one molecular reactant. And so therefore, the appearance is the concentration will no longer change. In this example, K is greater than 1 because you have more products than reactants at equilibrium. The other graph you might have to kind of generate is rate versus time. And the slight difference here is, yes, the rate decreases, and yes, the rate increases, but they should merge. So rate versus time, the rates should merge. Concentration versus time, they do not necessarily merge. In fact, they usually don't. So that's the major graph that I think about with this, with equilibrium. They might ask you to sketch it. They may ask you, yeah, like they would probably be something sketched where you don't have numerical values, but you show general shapes. The rate versus time doesn't have to be curved. It could be a straight line. I'm just drawing it curved because the other one was curved as well. But all that matters is that the lines converge and stay merged together at equilibrium. So it could be straight lines. It could be something like this and like that. And that would work fine as well. It doesn't have to be a curve. Okay. Questions on that? Okay. Another higher level topic, 18. And that is a titration curve, okay? Understanding a titration curve goes down to kind of a lot of different aspects, okay? One, you have your pH versus volume, I guess for our purposes, base added, okay? Volume of base added here, okay? And you'll get a weak acid here. Where the equivalence point is above 7, because a strong base with a weak acid has equivalence above 7. A strong base and a strong acid, 7. A strong acid and weak base, less than 7. Okay. So the equivalence point is important because that helps you figure out the volume needed to neutralize, which can then help you calculate the molarity of the unknown acid. Okay. But also, when you get half of that volume, for a weak acid at least, your pH is equal to pKa. Okay, so that's an important concept as well. So understanding pH equals pKa. Now, because it's a weak acid, at this point, and this was something that showed up on the mock exam, is about like what's the most abundant. Now, in your notes, we did have kind of bar graphs to this, but I wanted to address this in terms of the acid and only the acid alone. And so here, all you have majority of is just HA, because a weak acid doesn't dissociate very much. At this point, you have the same amount of HA as you do A minus. That's why the pH equals pKa there, because when you do the Rice chart, those two values cancel and all you're left with is Ka and H plus. At this point, all you have left is A minus, because all of the acid has been neutralized and you're left with just an abundance of A minus. So as you go progress from point 1 to 2 to 3, the amount of HA decreases because you're neutralizing it, and the amount of A minus increases because you're producing it when you neutralize it. And so the abundance of those species becomes significant. So A minus becomes significant after you start adding base. And namely, this section here, which we call the buffer region. Okay, that section that resists pH change when small amounts of acid or base are added, That's your buffer region, because a buffer region has to have a significant amount of a weak acid or weak base and a significant amount of its conjugate. And so in this region, you have enough HA and A minus that you can act as a buffer. Also, if this is flipped, POH could equal PKB as well. Like if you're doing a weak base with a strong acid and it's like titration curve downward, you could solve for the KB of the weak base as well. And make sure that your indicator changes color in that region of the equivalence point. That's the whole purpose of having an indicator as a visual guide. Okay. The last set of charts and graphs and tables that I think you'll look at, other than some of the ones that are in data booklet, is topic 11 and 21, okay, which is the idea of mass spec, IR spec, and NMR, and things like that, okay? And so what we're looking at here are a couple of things. Mass spectroscopy, okay? And so a mass spectroscopy has certain components here that you have to be able to identify. And again, we're not going to go too much into the calculations. I just want you to be able to identify and recognize these things to interpret, and then you can kind of apply things later on. Okay. Parts of this that you need to know. This significant peak at the rightmost is the parent ion peak. I'm just going to make the substance A for that purposes. And remember, if you show up on a peak here, it's always a positive charge. Okay. If they ask you what species represents that peak, you write the whole molecule and then a plus one charge at the end of it. And then these are fragments of that original molecule A based on losing different pieces by measuring that. Okay, so mass spectroscopy uses mass to charge ratio to identify what species are showing up in the compound. It's really only useful for like empirical, like molecular formula mass. And maybe eliminating some possible isomers from the structure. Okay. IR spectroscopy, using infrared to measure bond types by absorbance. Okay, so with IR spectroscopy, you have this thing, they'll call it transmittance, they'll call it absorbance, whatever you want. But the idea is that when there's absorbance happening, you get different types of bonds. And so you'll see a bond here, and a bond that is represented here. Don't forget, this 1500 or less is the fingerprint region, which is usually not useful for independent bonds, but you could look at the pattern overall to identify similar structures for that. So IR spectroscopy, you're reading wave number. Okay, which is centimeters to -1, which is like 1 over wavelength. Okay, HNMR I'm going to spend a little bit of time on because there's like 4 aspects of HNMR, especially in higher level, that you have to know to be able to identify the structure from this. And so we're going to look at an HNMR and break it down into what's important and what is not important. I love this one. Don't. Oh, actually, maybe that one is okay. That one's just kind of hard to read. I was trying to find one that. We'll use this one. It's fine. Okay. This is an NMR spec. And so this uses radio frequencies for the hydrogen environments. And we're going to talk about each of the aspects that are on this graph here. One, namely TMS. Okay, at 0, that's TMS. Okay, now, each of these here, maybe I don't want to circle them, but this is a hydrogen environment or a set of peaks. Okay, so this molecule here has 5 hydrogen environments here. Okay, has 5 hydrogen environments. So the number of sets of peaks, that's important for that. How many different hydrogen environments do I have in the structure? Okay. 2, these here are called the integrated traces. And the length helps you find the ratio of hydrogens in each environment. It might be a reduced ratio, so you'll measure each line and look at the lengths of it and then find the ratio between those lengths. It's usually a pretty straightforward number. So you would need a ruler to measure those traces. Okay. So the integrated trace is the area underneath the curve that tells you how many hydrogens relatively are present in there. This down here is the chemical shift. And so what that tells you is the type of hydrogen functional group you have. And if you refer to the tables in the data booklet, there's a whole list of them with a bolded hydrogen. If you look here, they give you a list of all this HNMR, and you'll notice if you look very closely that there is a bolded hydrogen in question here. So really pay attention to which hydrogen is bolded so that you make sure that you're able to identify it. To be honest with you, I think there are a couple where there's more than one hydrogen, but for the most part, they try to do it as only one hydrogen in each table so you don't get confused. And the last thing is a splitting pattern, okay? And the splitting pattern, the way it's calculated is neighbor hydrogens plus 1. So however many neighboring hydrogens on neighboring carbons there are, that would be, that number plus 1 is the neighboring hydrogens. So you could have a singlet where you have 0. You could have a doublet where you have 1. A triplet where you have 2 neighboring hydrogens. And a quartet where you have 3 neighboring hydrogens. And so just to make sure this is not related to NMR, but I just want to make sure that we are on the right page here. Okay. Because this is asymmetrical, you'll see, oops, sorry, I missed a hydrogen. A lot of different environments here. Okay. One environment here. One environment here. This environment here. This environment here. Oops, wrong color. And this environment here. So there's actually 5 different environments in this structure because it's not symmetrical, so the end ones aren't the same. If you look at this blue section, it has 1 neighboring hydrogen, so its splitting pattern would be a doublet. This OH would be a singlet because it's bonded to oxygen and not a neighboring carbon. This, oddly enough, would have a 6 for a splitting pattern. I didn't think about this when I drew the structure because it has 5 neighboring hydrogens, the 3 in the blue and the 2 in the green, so it would have a 6. You don't have to know the name of that. It's a sextet, but that's how you would figure it out. This green one has 4, so that's a 5 splitting pattern, and this red one has 2, so that's a triplet. Now, if you have multiple of the same environment, you just look at the neighboring hydrogens next to one section of that environment. Don't look at total number of hydrogens next to it. Just go, okay, these ends are the same environment. Well, pick one end, look at its neighboring hydrogens, that's a splitting pattern. Don't look at both neighboring hydrogens for both of them. Just look at one of the 2, and then that will help you figure out the number of splitting, the splitting pattern here. So analyzing this, knowing all 4 parts of it, splitting pattern, integrated trace, sets of peaks, and then the chemical shift will help you maximize your points. And it helps you eliminate isomers, right? Like the idea here is that you might have 2 possible isomers and they have different number of environments, or they have different shifts, or they have different splitting patterns, and that will be reflected in your NMR spectroscopy. Questions about that? I'm going to switch over here and show a couple of different things in here that are in your data. Well, actually, no, we already talked about it in data booklet. So I think you can use that for you look at that in a different video. But any questions on any of those charts, tables, and graphs?
Mr. Charlie?
Yes, Erica.
Back to the mass spectroscopy graph. So we have to always include the positive charge, except for, are there any like exceptions to that? Because some questions.
Yeah, so if they ask you for the fragment lost, Erica, you don't write the charge.
Yeah, perfect. Thank you.
Right. So yeah, if they say identify the fragment lost, you just write the fragment. But if they say identify the fragment responsible for that peak, then you have to put the positive charge, because only positive charge species can be responsible for peaks in the mass spec.
Okay.
Okay, good question. Okay. That's it. We finished with a little bit more time than I thought. And so that's your kind of 2-hour review of tables, charts, and graphs. A lot of these tables early on in trends and stuff like that and graphs, those are really popular for multiple choice questions and seeing if you really understand it or if you've just memorized increase or decrease across a periodic table or down a group. And so those ideas in graphical form are very challenging for students that don't understand the concepts themselves. But this is our last Saturday session for the year. best of luck to all of y'all revising for your IB exams, and hope all my videos from this year help you review and help you be successful on the chemistry exam. So thank y'all.